Welcome everyone to the parallel session today. It's a great pleasure to have David Osten from University of Wrocław. Please.
Thank you. Thank you for coming to session and also my talk on integrability. So I know it's not really the main focus of this conference in total. But I guess in many of the topics we have heard also in the plenary sessions always comes up, and many of the interesting things work because the underlying theories are integrable. So I'm concerned with understanding integrability as for itself a bit better, so mainly looking for what are there for other integrable theories, so on, and I will even do the more simple setup of classic integrability. So maybe let's give a quick motivation overview about integrability in string and field theory in general. So in general, interacting field theories and also quantum field theories, of course, are very hard. And what is one way how one deals with this in physics is often one looks at toy models, so one which maybe shares some features but by chance might be solvable. Okay, and maybe one example would be QCD. It's a very important theory, but it's not solvable, but in some sense, so a gauge theory which is integrable exists, and this is n equals 4 square mils. And we have heard a lot about talks about actually calculating things which one couldn't do in this detail in QCD. So what I mean, in particular, we'll look at a particular subclass of models, sigma models, and look in which case these are integrable. And sigma models are actually relevant in a lot of areas of physics, so of course in particle physics and in string theory, but also in condensed matter and gravity. And so I would say that integrability you could consider this as an third important symmetry principle in string theory, besides conformal and supersymmetry. Because typically if you learn string theory in a lecture, you look at the integrable case, namely free series, but maybe also more non-trivial case where you can still do all the computations. In particular, this would be the superstrings in flat space, but also very relevantly the superstring in ADS 5 crosses 5 or other very symmetric backgrounds. And this probably led to the most famous results of integrability 20 years ago and ongoing, that basically with that one can really try to prove ADS-CFT by computing things exactly in the string theory and computing things exactly in n equals 4 square mils. But so these are very symmetric backgrounds, but it turned out that in general sigma models in symmetric spaces like flat space or ADS5 or spheres are integrable, but also certain deformations exist. Okay, so let's say what integrability actually means, or how to formalize it. So in a system with finitely many degrees of freedom, it's quite clear. You would call a system integrable if it has as many degrees of freedom as it has conserved charges. So you can basically just integrate the system. For field theories, this is of course a bit hard because you have infinitely many degrees of freedom, but there's some underlying formalisms which you can use. And typically, this means because you have infinitely many conserved charges in the field theory, you would have a lot of hidden symmetries that are somehow realized. And of course, the standard example is actually the one I'm interested in. These are sigma models. And just to compare, there's also, of course, the concept of quantum integrability, which is not directly related, which is that you would typically call a theory quantum integrable if you can use so-called exact S matrices. So basically, all processes factorize into 2-to-2 scattering, and then there's some consistency conditions between these S matrices. And the standard examples and reviews would truly be spin chains, or the planar limit of n equals 4 superangles. And yeah, so why be interested in this very general questions of integral theories? So first of all, some very basic questions are not clear. So for example, it is not really clear what is the relationship between classical integrability and quantum integrability. So for example, n equals 4 superangles is quantum integrable, but not classically integrable. And as whether there's theories, for example, for these sigma models, they are known to be classically integrable, but it's not clear how to, in general, make a quantization of these theories which makes use of the integrable structure. So, not even for simple toy models. So there are simpler toy models than sigma models where this is known, but in general, this relationship is not known. And related to that, even I think an easier question. So classical integrability is, of course, a relatively easy question to ask conceptually. You don't need to do quantum theory. But even this space, even in a very restricted setting of sigma models, it's not clear what the total full classification of integrable sigma models is. So one always finds new sigma models here and there. And in particular, what will be the main message of my talk is that also the heterotic string, which hasn't been considered as an integrable system, is also a classically integrable system. Okay, and so the other thing is that typically the integrable models, they have, like the superstring flat space, 85 versus 5, they have a lot of obvious symmetry. So a lot of supersymmetry, a lot of killing vectors in these backgrounds. And one might ask, maybe one would like to have integrable toy models that have less of the symmetry. And so this is also something which is done in this field to basically look at deformations of these very symmetric setups which have less symmetry but still preserve classical integrability, because it's clear the hidden symmetries are anyway much larger than these obvious symmetries. Okay. So maybe are there any questions until here? I'm happy to spend more time here because it's clear that I'm happy if we just talk a bit about integrability, and then I will at the end go into details.
So if you have a classical system,
Yeah.
if you have a system that has classical integrability,
Yeah.
is there any criterion to check if it has automatically quantum integrability if you quantize it?
So no. So there was, in the 80s there was this program of inverse scattering method, so the Russian school of integrability, as we would often call it, and this was a prescription of going from classical integrable system to a quantum integrable system, which is true, but it only works for a very restrictive set of models, and sigma models, for example, are not of this case. So for example, the Gross-Neveu model is one of the models which looks very similar to a sigma model but is a bit simpler, and but in general there's some ambiguities going there. So one thing which recently became both popular in the classical integrability and the quantum integrability is so-called spectral curve. So some underlying algebraic object which can be used to calculate the spectrum of objects here and there. And it seems that maybe these, in this sense, there might be an obvious relation. And there are some mathematical objects so there's some underlying objects which are called like a classical R matrix, I will play a little bit, and there's a quantum R matrix, and there's, in some obvious sense, these objects are related, but how they are really related in the physical sense is not clear. So then sometimes the objects are not a classical limit. And for example, for n equals superangles, if you look at this object, the so-called R matrix, and you do the classical limit, this will not reproduce integrable structure. So there's some formalism, but other questions? Yeah, please.
So we do know that heterotic string theory, both of them are connected by dualities to other string theories.
Yeah.
So is integrability a property that translates through duality?
Very, very good, very good. I mean, I will actually comment later on it. So actually a lot of these deformations are related to T-duality transformations, because T-duality basically stays at fixed order in G string, and then you basically, with T-dual transformations, you also map sigma models to sigma models, and basic T-duality on the sigma model level means that two sigma models are classically equivalent. So you can make this, but S-duality, which I actually working also on that, but not in this context. I try also to see if S-duality could be considered as, so for example, if you look at the string sigma model and the D1 sigma model, you could imagine that S-duality transformation, which map to one to the other, might preserve integrability, but only for the string sigma model, integrability has been considered. Okay, yeah, I will introduce the formalism of integrability soon. So on this talk, I will just briefly, basically this is the bottom line. I will talk about classical integrability. I will find a new classical integral model, and this will be the heterotic string. So I'm happy if this is the bottom line. So I will very briefly explain to you the formalism of classical integrability, then go to the way how I constructed this new model, and then depending on time going into some technical details, but they will not be very relevant, I think. Okay, so let's introduce the formalism behind classical integrability, and basically, so this was invented by a mathematician called Lux, and he has basically made a formalism how to construct for a certain subset of theories infinitely many conserved commuting charges. So commuting means that they are kind of independent and that they are good enough to basically restrict theory. And how one does this is a classical theory, one even has this theory just on the level of equations of motion, this is enough, and the underlying object is so-called Lux pair, which is a one form on the worldsheet or on the 2D spacetime, which depends on some complex number, and typically it also is valued in some auxiliary Lie algebra, which underlies the system. Okay, and then the condition is that this Lux connection has to be flat, and that this Lux connection, if you look at it for all values of spectral parameter, is equivalent to the equations of motion. And if you have this, then you can actually show that this object, the monodromy matrix, which is basically a path-ordered exponential of the one component, also of the spatial component of this one form, that this is conserved in time. And so you can also look at objects like that. So this is the trace in this auxiliary Lie algebra. And then you get basically an infinitely many conserved charges, because you can expand this object in this auxiliary parameter. And so all these Q's would be conserved charges, and there would be infinitely many of them. Okay, and then you have to still check that all these charges you get are in involution, so that they are independent. So basically that their Poisson brackets vanish. Okay, and this you do you check the Poisson bracket of this Lux operator, and you show that basically you have a commutator of this object with an object in G, tensor G. So it is phrased in a very efficient way, but in the end it's just commutators of Lie algebra, and you just use that the Poisson bracket would be commutator in the Lie algebra. Okay, are there any questions to that? Good. And maybe just as a comment, so this would be one way to show integrability. If you want to show that a theory is not integrable, then you would typically look at a reduced version of the model, make some ansatz, so get a finite-dimensional system, and often if it would not be integrable, even this very simple system would already be chaotic. So this is how you would prove non-integrability. Okay, and in this talk, or in general for this, what I want to do, normally you calculate Lux pair if you want to have an integrable system, and you would have to compute this object R. Okay, so what integral models are there? So there's the Westerminier-Witten model, there's the principal chiral model, and then there's generalizations of these things, which basically would, for example, be sigma models in symmetric spaces, for example, for flat space or ADS. And then there's a bunch of deformations of these things which break these things but conserve integrability. And there's a lot of different guiding principles to construct such theories. So one very popular one is to reduce from some higher dimensional topological or integral theories and just reduce to 2 dimensions. And as I said, you can somehow deform and want still to have such a flat Lax connection. And there's some algebraic tools, and this latter one is called E-models, which is based on the Hamiltonian formulation of models I will use. So this was some work introduced recently, that actually you have this formalism also applicable to heterotic sigma models. So what I did in this recent project is to embed these well-known integrable models into an heterotic sigma model and then also do a deformation of this. Okay, and the underlying formula I use is actually a connection of duality symmetry and sigma models, so I'm very happy about this question, is that actually generalized geometry, which is the geometry which formalizes T-duality symmetry, is actually very useful language in sigma models. So how does that look? We look at the Hamiltonian formulation of sigma models. We will have some currents as phase space variables, and they will be valued in some representation of G, which is the underlying duality group. We'll have a current algebra, which is basically the Poisson brackets, which for sigma models looks like that. So where we have a term with delta prime, so these the sigmas are the spatial coordinates, and so we have some object in front of delta prime, which is an invariant of the duality group, and then we have basically the sigma model itself is described by these structure constants. And just as a comment, so actually this delta prime term is what makes sigma models very complicated in comparison to, for example, the Grosvenor model, where this would be 0. Okay, and then the Hamiltonian would be quadratic in these currents and characterized by something called the generalized metric. It's not so important right now. And if you look, so what is this duality group? Basically for the bosonic string it would be the T-duality group. For brane sigma models you could use the exceptional groups, and for the heterotic string you would use a group like that. So OD plus N, D. Why is that? So basically you parameterize your phase space as follows. You have your coordinate fields. Of these you have D. Then you have the canonical momenta, with also D of those. And then for the heterotic sigma model you have like N chiral currents in addition. So this is these currents just take values in the fundamental representation of OD plus N, N. And then in order to derive these values, you make some field theory definition in order to arrive at this form. Okay. And basically, so for the heterotic sigma model, you would, this is just so here I just introduced the heterotic, the bosonic part of the heterotic sigma model. You can extend this to the superstring. Okay, so how is this coupling to the sigma model background, to the supergravity background described here? Basically, you would typically describe your heterotic supergravity background, so the coupling of sigma model to some background as follows, via a metric G, a B field, and heterotic gauge field. Yes. And here, basically, you in these with these big indices, d plus n, comma d indices, you make a decomposition, and basically some of these coefficients will correspond to the H flux, some will correspond to these hologicity coefficients of this frame, and some will correspond to the field strength. So it couples not to B, G, and A, but it couples to these basically field strengths of these objects. Okay, and then explicitly the current algebra would look like that. And so far everything was general for arbitrary backgrounds. The so-called E model, which I use, is basically that we have constant fluxes, so this would be then some kind of Lie algebra fluxes of some big underlying Lie algebra. And yeah, the Hamiltonian would look very canonical. Okay, I will go very briefly through the rest. So basically, you can embed the principal chiral model, which would just have this metric coefficients inside, and then you can phrase the equations of motion like that, which already look very close to a zero curvature condition, and it turns out indeed you can find a Lux representation of these objects. And it also turns out you can find a classical R matrix for this object. So you phrase in this connection, you put these currents of the principal chiral model, and you have this spectral parameter, and if you look at this zero curvature condition, you will reproduce the different orders of lambda, you will reproduce these equations of motion. So this would be the chirality condition, this would be the real equation of motion, and this would be just the Varro-Cartan condition on these forms. Okay, and so this is basically a trivial that you can include. So this would be a heterotic string moving on a group G plus some abelian chiral currents. So this is kind of trivial that this is integrable because you have an ordinary sigma model, which is, you know, integral, and some additional chiral currents. But so I showed that you can introduce some choice of gauge field, heterotic gauge field, to make as a non-trivial heterotic string background and still make it integrable. So this is basically you have to take the A in this group of the principal chiral model and basically arrives at the following fluxes, for which this integrable model would be integrable. So basically you have some kind of H flux, which would be structure constant like in the Westermino model, and you would have basically that the field strength of this heterotic gauge field would be also proportional to these fluxes, and in this case, the equations of motion look at that, and one can find a Lux connection to this case as well. Okay. Integrability is always very technical, so I will maybe skip these technical details and just show you that you can find the R matrix. And so the important thing is, so we have found some new integral model, and then the question is always, if you look at these deformations of string sigma models, would be this deformation also a string sigma model? If you make some random geometric deformation, it might not be a heterotic supergravity background, but I've shown that this deformed background is as well heterotic supergravity background, and this you basically look at the supergravity equations of motion and see that you have to introduce a certain deformation of your this abelian field strength, and in the end it turns out you have to modify the coefficient in front of the Westermino term in order to compensate this in the supergravity equations of motion. So maybe this is enough for this talk. So we have shown, so hope I have introduced a bit of integrability to you, and I've shown that the heterotic string can be considered as an integral model, and also that there's a non-trivial heterotic supergravity background in which the heterotic string is integrable, not just flat space. Thank you.
Questions for David?
So you mentioned that if you start from a higher dimensional theory,
Yeah.
you can construct integrable models. So we do know about heterotic theory that it comes from compactification on S1 mod Z2 from M theory. Oh,
Sorry.
sure, no
Yes.
problem. Okay, so can it happen that you can get heterotic EE model that you just described from a dimensional reduction?
So, I mean, the cases I meant in this case, it was not very clear. It would be reductions. So the typical examples of the historic is that you have anti-self dual Young-Mills, or anti-self dual gravity in 4 dimensions, which is integrable, and then you can construct a lot of known theories. Basically, all Sigma models in 2 dimensions are as reductions of 4-dimensional. So these reductions I meant would be you would have a 4-dimensional world volume and you would reduce that dimensionally. So this was what I was referring to. The other thing is, of course, true. If you have a bigger known integrable theory, you can try to make some truncations in some sense to keep the integrability. So yeah, I mean, this is a bit related to the fact that these duality transformations might keep integrability.
Okay, thank you.
Other questions?
Maybe I can ask a stupid question. I know nothing about integrability, but just because of association of terms. You mentioned this lax connection. Is there any way of phrasing this in the language of fiber bundles or principal bundles?
I mean, in principle, this lax connection is mathematically difficult object because, so I think more mathematical people than me, they would normally, so they wouldn't say it's like valued in Lie algebra, they would say it is valued in kind of an affine algebra because you have this complex parameter. Yeah. So basically you could better say that this is valued in a fine algebra, and then everything gets very hard because I don't know if there's a theory of there's not really a group to it's not an easy way to make a group to an affine algebra, and then this would be the group you would need for a principal bundle with that. So in this sense, yeah, it's a bit harder. So of course you can phrase this, you can phrase everything in a very nice covariant way, keeping this parameter, but if you want to make it very formal, I think it's hard to phrase it as a principal connection of, because you have this affine group, actually, affine algebra.
I also have an idea. So if you think about this thing, catches it, the worldsheet theory, yes, from the microscopic point of view, then there is a target space. Then whatever that manifold is, that will be reflected in the integrability equations. That
I mean, so for example, if you have look at so the principal chiral model would be, for example, a string worldsheet moving in a Lie group. So for example, ADS3, string and moving ADS3 is the principal chiral model with group being SL2. And in this sense, the target space geometry then would be recognize the fact that this would be SL2, and this whole Lie algebra would be valued, this whole lax connection would be valued in that. And for a more complicated geometry, which is not where, I mean, a lot of these things where we try to break this this symmetry, still there would be this underlying symmetry, but this lax connection would be different, and it is not. So this is actually also a question: what is directly the so in this. This is why I like this formalism. So in this formalism, you see in this current algebra, here you see the background geometry. But in the lax connection, if you have an integral model and you phrase lax connection in terms of these J, it becomes not as obvious as here. But here the target space geometry is exactly here.
Thank you. Okay, in view of time, maybe we can thank David for the nice talk. Thank you.